over here, and the microphone seems to be working. Zoomland, can you hear me? And we're going to replace files information. And we're going to wonder what happened to. All right, that works. That works. And Zoomland has said nothing. Actually, it probably said yes. Emmanuel was very generous. Thank you, Emmanuel. Appreciate that. And we see 8. There we go. And I'm just going to show you one thing. We don't have to really elaborate in it, but I'm going to encourage you to grab the code. Though, of course, you also do have these notes. Again, with the notes, the only thing I take out are the questions I ask. And then let's pull this down. So you can also run a post hoc permutation test. To do that, you need the package rcompanion, but it's very straightforward to do. And that is you run your model, y by x. The function is called pairwise permutation test. And then the method is FDR. And what FDR does is not remind you of Franklin Delano Roosevelt, cool guy that he was. What it actually does is it does what we want in a post hoc, and that is it penalizes your p-value with each additional test that you do. The post hoc result is the exact same that we saw before, in the sense that you get that layout of, let's copy that. Let's go back here. Let's hope that we actually have the right stuff in. We do. And we have our R companion right here. I'm just going to run it so you guys can just see it. That's high floating menu. When you get that stop sign, what does that mean? Right here. Get a little stop sign down your console right next to the broom. What does that mean? It's running. And sometimes, if you're like me, a person who has very little patience, you'll get annoyed. Just let it run unless it goes on for a half hour more. It goes on for a half hour, you've got a loop, you've got a bug, just stop it at that point, or you get the stop sign. If you don't have that, it's just no big deal. You just continue to let it run. Another thing that I'll make mention to you is a lot of times language that you develop changes and it becomes deprecated. Deprecated in software language coding means that the actual function is being sunsetted or has been sunsetted. So when something becomes deprecated, it no longer works or it's no longer going to be supported. Like as an example, can you actually run with like an iPhone 3 or 4 anymore? For third and fourth generations of iPhones? The answer is no. You can make it work, but if there's any error in the code, they will not work anymore unless you can hack into it and modify it yourself because it is no longer supported. Apple will no longer adjust it. One of the things that happened over the weekend, to my knowledge, and that I did not notice this before, is in line underscore or element underscore line, size is no longer utilized. Instead, it is now line width. It's still working right now, but you might see this every once in a while, especially if you come back to old code where something becomes deprecated. This once happened 2 years ago where I used to use a function called factor as a way of cleaning up, as a way of reordering things or in order identifying what a factor was versus what a character was. And it was deprecated, but it was no longer supported. But I was teaching, but I didn't know that it was deprecated until I actually tried to run the code in the class and it stopped. That happens. You'll just notice a line down here normally that gives you some heads up so you can make the adjustment. So I'm going to take my line width. I'm going to copy that. I'm going to paste it into my code. I'm going to run it again. Doesn't really matter. But now at least I have code that is appropriate for it. And I could save the previous version and we're all good. Questions with that? Just running through dog habituations, just to get us down to that last part. This stuff earlier. And now let's look at we run that line of code, and that gives us the same post hoc test that we saw before, where we have our adjusted p-values over here. And then you could define which of those adjusted p-values are less than 0.05, so that you could describe the comparison like food and grab as being different. For food and grab, the adjusted p-value is 0.000149. All right? And while you certainly can look at figures, and I would encourage you to look at figures to make these comparisons between the treatments, the post hoc is a very nice way to confirm the patterns that you are seeing. Any questions with that? Any questions with the exam? Please remember, there is a late penalty if you turn it in late. That's not a big deal. The big concern is if you don't turn it in, that is a big deal. So please make sure that I know, and if there's a mitigating circumstance, make sure that I know that too. I figure we're professional, and things happen all the time when you're a professional where you just can't get something done. It's no big deal. You just make sure you take responsibility, reach out, you explain it, and you get it done when you say you can. But just make sure that you do. Cool? Start grading them. The closed books, I've gotten about 2/3 of the way done. They're cool. And the open books, I think I've graded 2 or 3. And they're variable. That's good. I don't expect to be able to do any grading until the weekend at this point. Weekend's the next time I expect to be able to get on it. In addition, I've started opening up optional homeworks. They will not be graded, but they are very good things to do, practice through. I gave you script, and a script works completely for all of it. I gave you notes in those scripts. Don't use it until you need to. And then do the comparison. But if you're going to do the optional homework, what you want to do is just sort of fire through, play through things. Don't hesitate to come by my office hours. Don't hesitate to come through Sean's office hours and sort of play around with things. And then last, and we'll either do this as a survey through Canvas or Mob Rule in class. And that is next week. We'll have at least one choose your own adventure, maybe 2, but at least one. And that choose your own, Sean, the choose your own adventure is going to be a choice between circular data and principal coordinate analysis. And it's going to be principal coordinate, not principal component. Whatever you prefer. And Sean's leading the rodeo in that day. Yeah, I'll be in the back just heckling and making faces to heighten any insecurity he might be feeling. Cool? All right, so I'll give 2 seconds to that. So you know the distinction between them in terms of making your choices. Circular data includes any data that does not have a beginning and an end. It is a circle. And when you have a circle, there's a very specific way in which you need to address the data because the beginning and the end of the circle are the same thing. On a straight line, if you go from 0 to 360 on a straight line, the 2 furthest points from each other are 0 and 360. And therefore, if you take the average of 2 numbers, 0 and 360, the average makes sense. It's in between, it's the middle, 180. But if you take that straight line and you make it a circle, and you still have 360 units, the beginning and the end, 0 and 360, are the same number. They're not the opposite ends, but they're the exact same number. And therefore, if you use traditional statistics and you take the average of those, you're not going to come up with the correct answer of 0. Instead, you're going to come up with 180, which is the exact opposite of where they actually lie in that circle. So there's some cool things. There's some cool trigonometry, but we're not going to worry about the trigonometry so much. We're going to worry about the fun things you get to do with the actual procedures to sort of understand the information. And a lot of biology are circles. And very often biology, we actually don't treat them as circles. And I've seen a number of published things that were just that as crazy because it didn't make any sense because it was not treated appropriately for what the data was. Most of the stuff we're talking about here is really kind of ethical decisions based on data structure. Circles are fundamentally different. And then principal component, principal coordinate analysis is a way in which you can evaluate traits that cannot be measured. You cannot measure size. It's not possible. There are many different indicators of size, but size by itself is not a single unit of measurement. I will use myself as an example. On one measure of size, I would be what is called vertically deficient. I'm short. I'm around a 15th percentile. On another measurement of size, I am ever expanding. I'm becoming larger and larger on a daily basis. And very soon I will become large. I think I am now an American medium, but the rest of the world, that is a good large to an extra large in terms of overall size. Which one of those two measurements are the appropriate measurement for size? And the answer is neither. They're both indicator of size. But sometimes you actually want to measure size. Sometimes you may want to measure, I don't know, intelligence or happiness. These are cool things to measure, but there is no direct measure for intelligence. Do you know someone who on one aspect is freaking brilliant, but on another aspect is a total fundamental moron? One of my favorite people on the planet, I just got to see this past Wednesday. Her name is Nicola Foote. She's one of the smartest people I have ever met. She is truly brilliant, just sort of working with her, listening to her, seeing the way that she comes up with ideas, seeing the way that she can work through documents and see these very important patterns. Every time I travel overseas with her, I now have to take her passport. Because when we travel overseas, she will lose her passport. And it's amazing the places where she can lose her passport. And she is a British citizen working in the United States. And that is something that you don't want to do when you are overseas in Ecuador, as an example, or even the UK, as an example. It causes problems. On one measure of intelligence, frickin' Einstein. On another measurement of intelligence, also Einstein. One time, celebratory, other time, inflammatory use of Einstein. Capiche? So principal component, principal coordinate analyses are ways in which we can figure out aspects of those characteristics that we cannot measure otherwise. So those would be your first two choices. Any questions with that? Yes, Madison? Your what won't run? Sean, can you party with Madison for a second? Oh, wrong computer. La, la, la. Okay. So we can save that. We can close that. We are not going to save that. We are going to close this. And we are now moving on to our next happy topic. I think I posted this. I'm 99% sure I posted this. And I hope I posted this. Okay. Two-way analyses build off the logic of a case sample analysis. And they end up being a really powerful tool for a variety of reasons. One, it can reduce the number of statistical tests you run when you are trying to understand the effect of multiple factors on a variable of interest. And that's good. Two, it can allow you to explore interaction terms, which is how a response variable, well, responds to the relationship between the first test variable and the second test variable. All that right now probably shouldn't make sense, but they're really kind of cool ways of thinking. So we already looked at the effect of education on lifespan, but you can also look at things like the effect of education and gender and the relationship between both of them in terms of lifetime earning. But we want to see what happens in terms of a response variable, the dependent variable, but we want to look at not only education, not only gender, but both of them together and the potential interaction. The effect of smoking behavior on political perspective, on the amount of weekly exercise. 3 weird things to go together, but dang almighty, do we get weird things emerging all the time? Where whether a person smokes or not, their political ideas and thoughts, and then how that associates with the exercise regime. The effect of detergent and water temperature on the ability to remove dirt from soiled clothes. And when we do our own wash, do we actually pick a temperature? No, we use ordinal data. We do low, medium, or high. It's associated with a continuous variable. Remember, it's ordinal. We just treat it as a category. So another thing about 2A ANOVAs is that they are functioning on the same structure of nominal and ordinal independent variables. Cool? A good example, and I like birds, so I choose a bird, is the effect of sex and food stress on the brain development and areas of the bird associated with song learning and song production. Song learning and song production is a relationship between a high vocal center area, RA, and this little nod down towards the brain stem. Song production, now song learning, song production is more of a pathway that includes both the high vocal center area X, which is kind of a weird name for some brain tissue, RA, DLM, and again, this little area in the brain stem. But what these researchers did is they looked at how these areas of the brains developed based on being male or female, where males do the singing in birds, females do not, and the association of food stress, and especially food stress at a young age, and then how that influenced the overall development. And there's some good examples, like, you could see differences between male and female, and that's not surprising. Again, considering males are the ones who produce the song, males and females in terms of both area X and HVC. That's not surprising, but then you can also see differences in terms of food stress. And it may not be surprising in this case that food stress is observed both in male, but then also female. You might expect in just males since they're the ones producing the song, but the overall volume of these areas is reduced when the animal experiences a lack of food. This is the type of place where a 2A ANOVA becomes a very useful tool in order to understand these relationships. Make sense? Okay. The math is actually very analogous and similar to what we talked about in K-sample tests, one-way ANOVAs. We're partitioning out our variation. This time we're partitioning out in 3 areas. The group effect of the first variable. This is called a main effect. The main effect of I. The group effect of the second variable. This is the second main effect. The main effect of beta J. And then the potential interaction between group 1 and group 2, the first variable and the second variable. The combination of these 3 terms makes up our between group variation. So we're in a K-sample test, we're only talking about this issue right here, our between group variation. Our between group variation is now broken up into 3 areas of consideration: 2 main effects, alpha I and beta J, and then the interaction between I and J. All 3 of them go into our between group measurements, and then we compare that relative to the error, the residual, the within group variation. So we're really using the same structure. We'll still have the same F-tests. We'll have the same issues of degrees of freedom. We'll have the same residuals. Interestingly, alpha I will have a degree of freedom that may or may not be similar to beta J. They may have their own degree of freedoms. And the interaction may have its own degree of freedom that is different than either of the 2 main effects. But the residuals will be the same degree of freedom across the board for all, because that is your within group Those are your data points. That is a reflection of your sample size. Does the logic behind the math make sense? Looking at three things: the first main effect, the second main effect, and their interaction. Now, visually, I find it a little bit easier to understand this than I do the mathematics. And this is what we're looking at visually. The soft I term for our original figure is describing males versus females, where in this case, we might have one group that's significantly higher than the other group. Or we might have a first group that's significantly smaller than the second group. Why? It could be anything. Maybe it's the volume of HVC. Maybe it's the amount of exercise. Maybe it is the lifetime earning. It's whatever you're measuring. But when you're talking about significant alpha I, the significant group effect, what we're talking about is there's that major difference along the x-axis. Beta is a difference along the figure legends. Well, there's no real difference here between the categories of your x-axis. The difference is that these green samples are much larger than the blue samples, or that the blue samples are much larger than the green samples. That is a main effect. That tends to be your second important test variable. Alpha tends to be the one you're most interested, beta tends to be the one you're secondarily interested. Sometimes alpha is the one that's obvious, beta the one the more interesting. So there could be different uses for it, but it should be intentional. And then last is the interaction. And this is the part that gets a little bit difficult to get our head around, but in many ways can be some of the most interesting things. And that is the relationship between these variables and their response variable depends on which groups we're talking about. So when we're talking about the first group right here, then blue is greater than green. But in the second condition, green is bigger than blue. Or in the alternative situation, in the first condition, green is larger than blue. Or in the second situation, blue is larger than green. Which of the responses is higher and which of the responses is lower depends on the interaction between the x-axis and the legend. Cool? Any questions with that? All right, good. Let's go to R. This occurred 10 years ago, I think. Sean, you dealt with this data, right? Awesome. So it's been a while. It's good. This was awesome in that sort of black comedy way. These are black and yellow banded millipedes. They're an exotic species in South Florida that showed up over by the Kleist Health Center, which is by the Kleist Welcome Center, which is by the food forest. And you have the food forest and the health center right next to each other. And during the early history of the university, and some of you all may have experienced this, the health center was one of our primary outreach areas, where we would bring in K through 12 students from Lee County, Collier County, Charlotte County onto campus to learn about public health and community health issues. A mosquito the size of a human being up on the wall. And kids would come in, third grade, fourth grade, eighth grade, to learn about health concerns in our area. Well, one fall, and I know it's fall because I was teaching animal behavior at the time, all of a sudden there was an explosion of these millipedes. And these millipedes went over to the Kleist Health Center, and they would get under the doorway of the Kleist Health Center so that there were thousands to 10,000 to potentially 100,000 millipedes inside the building every morning when they opened up. Now, you all can tell me, is a public health education space going to be excited about an invasive millipede all across their floors? No, they were not. They were pissed about these millipedes, and they were furious, and they were blaming everybody about these millipedes. So we got called in to try to figure out why there were so many millipedes. And every Monday, just to sort of finish off the story, there would be big trash cans full of swept up millipedes. Because our janitorial staff, the first thing they had to do every Monday was go clean out the millipedes from the space so the kids could come in and learn about public health where there are no small arthropods around to demonstrate in real fashion what life is. So this is awesome. We did a little experiment, and it was a clean, quick little experiment. It was a pairwise experiment where we did two things. We compared across the food forest, which was directly next to the clay center. And we put out pitfall traps at 6 different locations across the facility. We could not put it in front of the clay center because there is a road there. And though we tried to dig into the road to create a pitfall trap, it did not work, and nor did we receive that permission. So you guys know what a pitfall trap is? It literally says it. It is a small hole, you dig in the ground, you put a bucket, you put some oil so that when the animal falls into it, they just die at the bottom of it. And you collect the animals that fall into it. The first main effect we were interested in is, do these millipedes, are they found primarily around the food forest or the clay center? The clay center was throwing proverbial and literal arrows at the food forest, trying to burn it down on the assumption that that's where the millipedes were coming from. Let's find out. That's the first main effect. The second main effect was, are these millipedes attracted to light? So at each one of these locations, 1, 2, 3, 4, 5, and 6, we have put 2 pitfall traps. Both of them had a light attached to it. Each night, one of the lights was turned on and the other one was kept off. So we had one main effect, and that is the location, food forest versus play center. And we had a second main effect, and that was the issue of light or no light. And we were trying to figure out, 1, where are the millipedes coming from? And 2, are they attracted or are they dissuaded by the presence of light? Make sense? Cool. So what I want you guys to do is I want you to analyze it. Grab the millipede data set, take a look at the millipede data set before you do anything. And then, if you will, look at these 2 codes. There are 2 separate codes in here. One is when you're only looking for the main effect. And you're only looking for a main effect when you add a plus sign between your 2 test variables. So Y is a response variable, X is your first test variable, Z is your second test variable. When you only want to look at the main effects, you put a plus sign in between. When you want to look at their interactions, you put the asterisk in between. Please look at both procedures. Please look at the results of both procedures. Please write an appropriate result or result sentences that describe all of what you have learned. Cool? Make a project, load the packages, manipulate the data, do the things we always do. Record. Okay, we should be back in show. So I've done this before. Oh, wrong one. As a reminder, one of the things I do all the time is I just copy and paste a bunch of stuff, reuse it. Load our packages. Again, the only one that's going to be new today is Permuco. Yes. I don't know. We'll fix it as we go through the code. Yeah. But the only one new today right now is Permuco. You don't need it immediately, and we may not need it before the end of the day, but it is something we'll be working with later. The other ones we've used before, same as before, make sure that you actually change things into factors. And this is particularly true. You've got to do this in K-samples and in 2A ANOVAs because these are evaluating the effects of categorical variables on continuous data. So there's always going to be something that's got to be treated as a factor. We've done that before and we're happy with those. Again, I like to do the summary. Attach is very important when you only have one data frame you're working with. And we can see everything is looking good. We have both food forest, CLICE. You might want to reorganize this. I'm not going to worry about it because we're going to go into other stuff. If you forgot the code, to how to reorder this in location, you can find that on the optional homework. But I will ask, why would you want to reorganize the location where right now the order is both food forests placed? They're like both after food forests and place, but I would make an argument, that doesn't make sense to me. Why would you want to have a different order than both food forests placed? Where this is food forest, this is placed, this is both. You want it to match. You want it to match how you're presenting the information, how you're describing the information. So it should go either food forest both placed or placed both food forest. Whenever you can, use your tools to try to keep people sort of clear with what you're trying to explain, which was terribly unclear. So you're welcome. What's that phrase? Do as I do, not as I say. All right, so let's do our first one. You run it, and to that point, let's make this fit ME. Julie, very good observation. Make this fit ME so we can see both of them. Because all we're doing is looking at the main effects here. I copy and pasted these results directly into the script, and I like to do that so that if I need to go back and look at the results, I don't have to run everything again. I already have it. In addition, when I'm doing permutation tests, I like to do this so that I don't try to cheat when I get something squirrely, which is highly tempting, but it tries to help me be good. What are some things we can notice? And today we're just going to go in a straight order. Ashley, starting with you. Location. Are we going to describe the null or the alternative hypothesis when the effective location on this row is a small number? Alternative hypothesis. And when the p-value is small, we are comfortable with rejecting the null hypothesis. So we're going to describe these as a different. There's a difference in the location. Do we know where that difference is? No. And if you want to, I would always encourage you, make a plot. So run the analyses, but then make a plot, and you can use the visualization as a plot also to help you reinforce and remember what to do with the p-values. But the p-value is small, so we're going to describe the alternative. There is a difference between our locations. Jordan, what about the treatment effect? That p-value, is that small or large? It's very small. We're going to describe the alternative, or we're going to describe the null? We're going to describe the alternative. Are there differences between the treatment, or are the treatments similar? There are differences. Perfect. The p-value is small, so we're going to describe the alternative. So we're describing differences between the treatment. Do we know what they are yet? Nah. And this one, Lacey, do we know anything about the interaction between treatment and location? Nope. So you have a little notes down here. We have different degrees of freedom. We'll come back to this in a half a second. But what I want us to do is go to that point and let's actually take a look at the figure. I ran it. All right, there's some ugly code there that I'll have to fix out later. But you got the basic idea. Right. All right, that's a little better. Still pretty ugly. That's a little better. Madison. Let's get rid of that. Turn one more time. Okay, there we go. Is there a difference between treatment? Yep. We have the p-value. P-value is very small, 0.0001. Is there a difference between treatment? Absolutely. Are the millipedes responding to light? 100%. What are they doing in response to light? What's that? Increasing number. They're getting trapped in a pitfall trap. Are the millipedes attracted or dissuaded by light? Attracted. So if you were trying to help the Kleist Center, what advice would you give them? Turn off the lights. They had a light directly above the door closest to the food forest that they kept on all night. The students in animal behavior produced these data. We showed them the results. We told them all you got to do is turn off the lights. What did they say? No. I kid you not. Some people, you just can't help but turn off the lights. Is there a difference between, Jeffrey, the locations? Okay, let's go back. This was Ashley's first point. Let's go through here. Is there a difference between locations? Yes. Yes, there is a difference between locations. Now, based on looking at the figure, where were most of the millipedes? In both. Most of the millipedes were in both. So, and then followed by the food forest and then the Kleist Center. So, did the Kleist Center have a point in saying that the food forest might be the source of the millipedes? Sure. Did they have an effective strategy to reduce the number of millipedes that came inside the Kleist Center? Of course they did. What should they do? Turn off the lights. It's a very nice, simple thing. And did they do it? No, of course they did not. But that's not our job. Our job as scientists is not to require people to do something. Our job as scientists, in my philosophical opinion, is to provide evidence, provide context, and then let others make a choice. I think in many ways, we are best when we are able to just provide the evidence and then others decide what to do with it. Okay? But we need to provide the evidence. So we need to provide a result sentence. So, Misty, how many result sentences will you need at a minimum to describe this table? You need two. You have two separate tests, test of treatment and test of location. You need to address both of them. I generally like to write the first sentence to be the one that is most important or most interesting. The second sentence is either something that's sort of I expected, a control, or just not as influential or as interesting. So between these two, Misty, which sentence should be first? A sentence about the treatment, light or no light, or a sentence about the location, Kleist Center or food forest? I think that is totally fair if you're from the Kleist Center. But am I from the Kleist Center? No. What did I suggest people do? Turn off the light. Turn off the light. So you choose. Neither of those is the correct answer. They're both fine. You choose. You decide. But whatever you think is the most important, the most interesting, that's what you should prioritize. So if you, and Misty's completely on firm ground with this, makes the argument that the location is really what we need to be addressing, you start with the location. If you make the argument that light is really what we need to be addressing, then you do light. Either way, you've got to address both. So, Lauren, I would like a clean, beautiful, biologically oriented result sentence that describes the effect of location. Misty's argument. Oh my gosh almighty. Love it. There are more millipedes in the both location and food forest than the clay zone. Love it. Fabiola, what evidence do I need to provide? What's the obvious thing? What do we always start with? What do we always start with? Every time. You always start with this. It's kind of boring, but you got to start with it, and then you move on from there. For every test, we always start with the same thing at every test. Every test, all semester long. You got a bunch of people right next to you who are completely abandoning you. Yeah, so we always start with the p-value. So we start with the p-value. So we know we need to report the p-value. Okay, so we're going to report that. P equals 0.011. Fantastic. Jonathan, what evidence do we need to justify the p-value? And this is always the same thing, though it changes names with each test. It's always the same thing. We need the test statistic. And I'm fine with test name. Yep. And then we need the F value. And Jonathan, what's the F value? Perfect, 4.64. And one of the things that's very nice about what Jonathan did is notice which row it is. Each row has its own information. We have to deal with our row, our p-value, our F value for location. And then how many degrees of freedom am I going to report there, Victoria? Two and nope. Perfect. So in the evidence, we report the test statistic. We report both sets of degrees of freedom. One is about our main effect, that's 2. And the other one is about the residual, that's 112. If you remember, the first degree of freedom in an ANOVA describes essentially the number of treatments, K. In this case, we have 2 treatments, light and dark. And we take a degree of freedom with 2 treatments, it's number of groups minus 1. 2 minus 1, so we get 1. Oh, I'm sorry. This is location we're talking about. Scratch that. We have 3 locations. We have the food forest, we have both, and we have the Kleist Center. And when we take those 3 locations together, minus 1, you get 2 degrees of freedom. The residual degree of freedom is a little bit different. And that is you do n, your sample size, minus the sum of location degree of freedoms, the treatment degree of freedoms, minus 1. So our sample size is 116, 1 degree of freedom for location, 2 degree of freedoms for treatment, and then minus 1. You sum that up, 116 minus 4 gives you 112. Cool? Chandler, we have more information we need to describe. In addition, we have to actually write a result for the second main effect. Gabriella, give me all the evidence. Give me the evidence. In fact, I'm going to have you a different challenge and ask Fabiola. Give me the evidence from the beginning of what I would write to the end. Perfect. Perfect. When we do it to ANOVA, there's always going to be more than one sentence. When we do it to ANOVA, you need to describe all aspects of the model. When we're only addressing the main effect, there'll be at least 2 sentences. One that describes the first main effect and one that describes the second main effect. Yes, sir? No, it's a great question. The reason I'm using a semicolon, and it's just a little silly grammar thing, is because of degrees of freedom, there are 2 of them, and I need a comma there. So as not to confuse the issue, I use a semicolon between the test statistics, degrees of freedom, and the p-value, and then a comma between the 2 degrees of freedom. It's a very good question. It's a silly solution, but it works. It's, yeah. Connor? Yeah, thank you. I got too excited. Questions with that? Okay. So we can also look at the interaction terms. And honestly, the benefit of doing just the main effects is you reduce the number of tests being done, and therefore you reduce the chance of committing a type 1 error, the chance that you describe a pattern when you really should be describing the null. But the reality of the situation is this stuff gets cool when you deal with interaction terms. It's the exact same code. The only difference is that you put the asterisks instead of the plus sign. And let me do this. We run that. And what I want you to do is I want you to write now the result sentences. The figure doesn't change. It's the exact same figure. It applies in both situations. The patterns may or may not be the same. And now you also get to deal with an interaction. All right? I think you could probably do that in 3 minutes. Simple way to start writing this results section. Oh, I'm asking for a different thing. I don't like to think unless there's a reason for it. So I always like to find ways to make my life easier when I've already thought. Thank you. So why don't we start with that? Why don't we start with that? Because do the patterns change, Dana? No, not the beginning. So let's use it. And let's clean. All right, so Dana, before I take off from you, do we still have the situation of millipedes are more common in both in the food forest and the clay center? So does that first sentence still hold? Perfect. Does the evidence need to be modified? Great. Tell me what to do. Seven and 3, love it. Love it. So the residual degree of freedom changes. We'll come back to that in a second. What else? Which rounds to 0.011. So actually the p-value ends up being the same, but we made modifications. And I want us to adjust one thing. And I want you guys to get in the habit of this. If you have a figure, reference the figure. The test is important in some conditions, but the figure is always important. So if you're not writing a figure legend on top of your figure, and you're putting this in text, you want to reference the figure. If you're putting the results on top of the figure for like a poster, then that's moot. That doesn't matter. Love it. And Dan, before I let you go, why don't you finish off with the other part? Computer again. What about treatment? Did that change? Seven. It's small. It's small. Here, let's do this. Let's zoom in a touch. Make it a little bit larger. Okay, 7.2. And what else? Perfect. So Connor, are we done with our results? The nice thing about when you do ANOVAs, you got to deal with everything. Until we get a repeated fashion, we'll deal with that in a few seconds. But we're not done with the results. So we've done location, we've done treatment. Have we done the interaction? We have not done the interaction. How R shows you there's an interaction is with this. It gives you both main effects and then a colon or something in between. That's your interaction term. All right, Connor, do we have a random or biological pattern in terms of the interaction? We have a random. How do you know we have a random? P-value is above 0.05. So we always start with that p-value. We don't stop with it. It's not the end all. In fact, it's really not that interesting. It's just where you start. Where we started before just allowed us to then look at the figure and make some decisions about it, or allows us to look at a post hoc and make decisions about it. It's just when we start. So Julie, what's a very simple, clean result sentence that describes the interaction term? So what we're going to do is we're going to play a game. You give me one, we're going to the next person. We're going to try to make it more simple. So give me a full statement. Okay, someone's got to be 22. I think, to give you guys a statement, I got Dante. Dominique? I'm sorry, ahead. You're beating 22, not age. You're beating 22. About 13. Simpler. Or did not affect millipedes. Done. Done. Love it. A interaction between location and fact. Love it. So, Gil, give me the evidence. Love it. That's perfect. Yep. And here's the difference between what we've talked about before and what we're doing here. These result sentences that we have in the script, they're the type of sentence you would write in a paper, a lab report, a manuscript. In those cases, they are separated from the figure. So you need to identify which figure, but they're connected to the methodology where you would describe your data analysis, so you don't need to describe it now. Okay? In a situation where you are making like a poster, where your result sentence is directly connected to your figure, it's not connected to your methods, and therefore you tend to define what that test is. The other time you define tests is when you are changing your tests all over the place, but the test statistic looks the same. And that might be a case where you use a traditional ANOVA and a permutated ANOVA in different situations, as an example. Great question, Connor. Any other questions so far? Okay. So when we do 2A, you will always have a situation of describing more information. When you do a simple test, like a one-way ANOVA case sample test, you might say there is a difference, and then you use the next sentence to describe that difference. That's fine. And that's especially true as the K gets larger and you have multiple things. It's not just 3 groups, but it's like 10. Because you may want to describe different ones of those relationships. The dogs habituate slower to grab than they did to food. But they also appear to habituate slower to territorial invasion than they did to food. So the first sentence is just that there is a response, a treatment. And then you might subsequent sentences actually describe each of those responses. And that's fair. But when you have 2A ANOVAs or tests where there are multiple procedures embedded within the same test, you need to describe each one of those results. Make sense? Cool. All right. So, happy holidays. Great, let's move on. Permutation test. Can you do a non-parametric test with a 2A test? Of course you can. You can rank the crap out of things. And you may decide to make this part of your career. I definitely have. I like to cheat with stats all the time. And if it doesn't exist, I'll make it and just force it to work. I have to end up describing it in my methods. It's sort of very long data analysis to actually explain out how I'm doing a procedure, but that's cool. You're welcome to do that. You have to understand what your assumptions are. You have to understand the math, but you can create stuff all the time. It's just like creating a method. You're just doing it mathematically versus what you might do in the lab. You can do it. And I've created non-parametric approaches using ranking back when good stuff didn't exist, like as in computer sucked. I didn't work on a computer until I was 25. And you're still doing this stuff, but you do it by hand. You cheat. It's good. It's lovely. But we don't have to anymore. Let's see if we do a permutation. So do me a favor, grab the rattlesnake data. These are the rattlesnakes on campus. Our campus has a wonderful population of rattlesnakes everywhere on campus. You walk past them all the time. If you want to creep yourself out, I'll tell you exactly where they are. If you do not want to know, I will not tell you where they are. And you can just enjoy your life because they don't care about you. They're all over the place. And they're really, really common in a lot of places where students walk past them at high frequencies every single day. Do you really want to know? Yeah, you really want to know? Okay, you know the light that's right by the Union, City Union, that crosses the main loop road? You know when you go across and there's that little patch of saw palmettos right next to the turn signal? Where when you hit the little Q and it goes, walk, walk, don't walk, don't walk. Seriously, are you still walking? That sign, right, where you hit it? Right there in that patch. There's almost always a rattlesnake historically right there, right next to the road. They spend more than 60% of their time within 5 meters of where we walk, where we drive, where we spend our time. Why? We don't know. We just know they do. And it's cool. Oh no, it could be thermal regulation. It could be that they're also more reliable food sources. There are a variety of reasons why it may occur, but they definitely do. It also tends to be the highest ground. And if don't think if you guys have noticed this, Florida gets wet. And the only dry places in Florida are where we build. And animals that don't like water, and rattlesnakes do not like water, go to high places, which is where we build. Yeah. But there's never been a rattlesnake bite on campus. And there are very, very few roadkills with rattlesnakes. They don't actually go into our space. They go right next to it. All right, download it. Need LM perm. The code, exactly the same, except it is AOVP instead of AOV. What we are looking at here is we are looking at the potential effect of gender on snout vent length. Snout vent length is a standard unit of measurement for reptiles. We measure the distance between the nose and the genitalia. Snout vent. It's considered probably the most reliable or consistently used measure of size, but obviously, as I said earlier, it's not the only one, but it's one that you use regardless of the herp you're studying. So Connor is studying gopher tortoises, definitely uses it. This is work on rattlesnakes, definitely used. And we're looking at the effect of gender, males and females, relative to age, immature or adult animals. And we're looking at the interaction between the two of them in terms of development. What I want you to do the analyses in a new script, run it as a permutation in a new script, create a figure of these patterns in a new script. That does bring up a point. Connor, y'all like to change the question. Is one of the things I'm noticing quite a bit, both on homework assignments and exams. I ask you to please address this question. You're like, nah. And you do a question that you want. Okay, that's fine, but you've got to give me some heads up about what's going on. And then if you do change the question, you've got to change the question. I literally read someone's homework or test, I don't know, where they changed the question. They told me they were changing the question, and then they said the research question was, and they repeated what I gave in the actual prompt. So if you got to change the question, like Connor just changed the question, I said, please take a look at snout vent length relative to age and gender, and Connor's like, no, I'm not doing that. I'm looking at total length. Fine, but if you're going to change the question, make sure I know that you are changing the question. You guys love doing that with the hurricane data. Please tell me if hurricanes change after the turn of the century. And you're like, turn of the century is 1975. What? So just give me some heads up. I'm fine. That's cool. Just don't mess with me and think I actually understand numbers well enough to know that that is not the turn of the century. You're just saying you're a year before the bicentennial. And that's what you were most excited about. Why that would affect hurricanes, I don't know, but maybe there was a little bit too much patriotism going on. Make sure I know what you're doing. And then if you do change it, don't tell me you're doing what I told you to do, because you're not. You're doing what you want to do. Cool? We're good? Yeah? Excellent. Thank you. Okay, so we're here, right? And I'm just going to run through these. Oh, stupid microphone. Still. Thank you. Zoom in. You guys can hear me? So running through, we put in our packages, we run our DF, we get our names, we do some factors. There's a lot of data. I just selected the 3 I cared about right now. And I cared about snout length, age, and gender. Made age and gender a factor. Run a summary. I always like to run a summary just to know what the hell I'm doing. I noticed that I have 3 NAs. I'm not going to do drop NA. I'm only going to worry about that if my plot ends up being weird. Do our attach, doing our plot theme. Now we get into the juicy stuff. All right. Brilliant. Brilliant. Look at that. Picking up the bugs quickly. Joe, that was you? Dana, brilliant. Well played. Okay, so results, that's what we get. This was unexpected. This, when we did the initial analysis, was a boring analysis that we knew what the results were. Let's start with age. Which animals are going to be larger? Immature or adult animals? Come on. You do not need to know anything about rattlesnakes to answer this question. Which animals are going to be larger? Adults. So did we expect to see a pattern associated with age? We absolutely expected to see a pattern with age, and we saw it. Very low p-value. I don't even know if you need to plot it. I can plot it. Fine, I'll plot it. You're like, I don't believe you. Fine, I accept that. We plot it. We got all sorts of issues going on. What do we got going on? Plot the bloody thing. No, we don't want that. We don't want that. Bring up a few things. That's fine, fine. And let's do, was it my theme? Present. Okay. Oh, what is going on? Now, whatever it is not happy. Oh, stupid comments. And what else? Have we seen another stupid mistake? You know, we could just make this easier. Right? Remember that? That worked. That's cool. Wait. So did we expect anything with age? Of course not. We expected adults to be larger. That's boring. Did we expect anything with sex? Now, this is for our people who know their herps. There's sexual dimorphism. Who's larger? Females. And yet, oh my gosh, no, I'm not gonna do that. I'm not gonna do that. We're gonna do down here. Do L, not up arrow. Summary fit. Okay, there we go. You guys do know you can go into the console, and if you need to get a line back, all you have to do is just go into the console and hit up or down arrow, and it will just reload a previous line from the script. So I do the summary. Age, very small p-value. Small p-value, describe the alternative. There's a difference. Gender. Is that a small or large p-value? That's a large p-value. What does a large p-value mean? There's no difference. But we know in snakes, females are larger. We literally ran this assuming that would obviously be a small p-value because females are larger. Duh. And is that a large p-value? Is that what we expected? Oh, hell no. Those are my favorite days in science. When you get something that just doesn't make any fundamental sense. It's weird. That's not at all what we expected. Something's wrong. Maybe we don't know how to sex these animals. Of course we know how to sex these animals. Maybe we don't know how to measure these animals. Of course we know how to measure these animals. Something else is going on. So look at the interaction term. Is there an interaction term? Absolutely. Absolutely. Adult females are significantly larger. But females are significantly smaller. And therefore, we have an interaction term. Adult snakes, the female is larger. But in young snakes, the males are larger. Age is an influential factor. Adult animals are larger than immature animals. Gender by itself is not. But there is a significant interaction where adult females are larger than adult males, but young females are smaller than young males. Make sense? Okay. Start with the over-under. How many result sentences are you going to need? This is just going to be the last time, and we're not going to write them out. How many result sentences will you need? You're going to need one for age, right? You're going to need one for gender, right? How many for interaction? 3 is what I would argue. The first sentence will be, there is a significant interaction between age and sex, or there's a significant interaction between age and gender. That's where you put your statistical evidence. As adults, females were larger than males, period, or comma. But as young, males were larger than females. So it could be 2 interaction statements or 3. Make sense? Of course. Yeah, come on. Ah, really good question. Why don't I use a bar graph with this? In fact, this is such a good final exam question. Not that I know I would ask it, because I think I already forgot the question I promised you I was going to ask on the final, which if you know what it is, you may want to tell me, because that means you'll get it. Easy one. But why? I don't remember what the question I told you I was going to ask. So I'm literally asking after class. Tell me. But why is this a bar graph? And I gave you the hint by showing you the code for the statistical test. For the millipedes, there's a bar graph. Why? In this case, we are running a parametric procedure. In the millipede case, so you're right about the snakes. In the millipede case, we're running a parametric procedure. So we're claiming the data are normal, so represent them as bars. In this case, we are running a permutation test where we know they're not normal. We don't care that they're not normal. We're just dealing with the distribution as is, and therefore want a box plot. They should parallel each other. How you present the data should parallel how you analyze the data. They don't always, and sometimes it's just easier to run one versus the other, but that's why we did it. Yeah, because the data you're evaluating is based on the distribution of the data you measure. And therefore, a box plot actually gives you the distributions, where a bar graph does not, because it assumes normality. Any last question? Or two? Ladies and gentlemen, go home. Have a beautiful night. We'll see you on Thursday.